Our speaker is Sorawit, who is a PhD student at ETH Zurich in the Seminar for Statistics, co-advised by Jonas Peters and Nicholas Fester. His work focuses on causality and invariance and bringing those to create more robust machine learning. So I'm excited for today's talk. If you were at the talk last week or 2 weeks ago, our most recent one, we started talking about extrapolation a little bit more systematically in terms of how kind of these ideas in causal representation learning, identifiable representation learning, in this kind of whole area really is maybe at its core motivated by extrapolation, and now focusing on works that really highlight and emphasize that. So I think this is a great example of one of those works. And in terms of how we should progress for the talk today, basically, just try to keep the questions during the talk to clarifying questions. And then we'll kind of more open-ended discussion questions, hopefully have some time for at the end. Feel free to drop off at the end of the hour, but typically, we go over 5-10 minutes, however long the speaker and other audience members feel like staying around. And if you are able to, please turn on your video just so it's not Sorawit speaking to a ton of white names on black backgrounds. All right, Sorawit, take it away.
Thanks a lot for the introduction, and thanks to the organizers for the invitation. And yeah, so today I'm going to talk about the identifying representation for intervention extrapolation. This is joint work with Ilan, Pradeep, Nicholas, and Jonas. And recently we just presented at iClear. And so the motivation of this work, I think, as Scheller pointed out perfectly. So I guess everyone is sort of like familiar with causal representation learning, where we sort of assume that there's a causal mechanism that gives rise to high-dimensional observations such as text and images, text and or images. And the goal is to learn a representation that somehow reflect this underlying causal mechanisms. And the premise is that once we learn this identifiable representation, we want to use this to solve some complex downstream tasks. And most of prior works for us focus solely on the identifiability questions. There was some prior work that tried to also link to the concrete downstream tasks, but we think that maybe this is a bit lacking. So that's the main motivation, that we try to present a concrete downstream task and show that if we can learn this identifiable representation, then we can solve this non-trivial task. And the task that we consider is what we call representation learning for extrapolation, where we have outcome Y here. We have Z as a latent predictor, and we have X as observed features, where we obtain X by applying a nonlinear transformation to the latent predictor, and we have A as actions or treatments. You can also think A as some sort of perturbations, or if you're familiar with instrumental variables, then you can also think of A as instrument as well. And the goal is then to predict the effect of unseen interventions on A and on respect to the outcome Y. And what do I mean by this? We can see this simple example on the right-hand side here, where we have interventions on A in the x-axis. We have the outcome Y on the y-axis. And now we have training data in yellow, and we want to use this training data to predict what's happened to the mean of Y when we intervene outside the training support. So here the test support is outside the training support, and we want to be able to extrapolate this interventional effect. And clearly, if you just regressing Y on A, then you get this green line, then we don't know how to extrapolate. So our method on the blue line here, you can see that we can extrapolate successfully outside the training support. And the method consists of 2 steps. In the first step, we use information from the action and the observed feature X, A and X, to recover the latent predictor up to an affine transformation. And this is where the identifiability of the latent predictor comes in. And in the second step, once we obtain this identifiable representation, we will use that to construct an estimator for the quantity that we want to compute, which is the condition of y given to A. And to just put into some context, you can think of A as, for example, drug dosages. You can think of Y as health outcome. You can think of the latent predictor Z as some latent biological processes, and X is the observed biomarkers, and we may have some hidden confounder between the latent and the outcome. And now the idea is that now we want to know what's the effect of drug dosages on the health outcome, especially for those drug level of drug that we have not seen in the past. So we don't claim that we solved this problem like completely, but we just hope that in the future maybe people will pick it up and try to adapt our work to really solve this problem. But this is just put into some context.
So you mentioned average treatment effects. Do you also care about conditional average treatment effects given X, or is it just
Yeah, so we can also identify this term, the conditional mean given do A and conditional on X as well. So I think in some case we may also interested in that quantity. Yes, that's a good question. And yeah, so to first, I would like to just give you an intuition why we can do this extrapolation, and the best way to just first simplify in the setup where we actually observe the latent Z. And here, this is a simplified setup. We actually observe the latent predictor. And the goal is to, again, compute the condition mean of Y given to A, where A star lie outside the support of A. The main assumption that allows us to do this extrapolation is that the effect of A on Z is linear. So this is we have just linear transformation of A, and also M naught has full row rank. So these are 2 main assumptions that allow us to do this extrapolation, and the way that we can construct and to show that this quantity is identifiable is to use the method of control function in econometric literature. So we can first see that this is the quantity that we want to compute, and using the SCM, the structural causal model that we assume, then we have this identity by just using that V is exogenous. Sorry, by using that A is exogenous. So the action is exogenous, then we get this. And now we want to show that the right-hand side here, we can identify all the unknown quantities, namely M naught, V, and the function L here. And again, this function L can be nonlinear. So the only linear part that we assume is from A to Z, but this L can be nonlinear. So from A to Y, this is still a nonlinear function.
I think I can infer this from your setup, but just to make sure my understanding is correct, all of these variables can be vector valued, like the treatment and the outcome. Okay.
Yes, correct. And now we can, so we want to show that the right-hand side is all the unknown quantity can be identified for observational distribution. So now M naught can be identified by regressing the latent. So now we assume that we observe the latent, so we can regress this Z on A directly, and we get the M naught. And now we can then be identified by just subtracting Z, subtracting M naught A from Z. And this is what people in econometric call control variable. And this control variable we can then use to help us identify the last component, which is the nonlinear function L. And the way that we can see is that if we look at the conditional mean of Y given Z and V here, we can see that under our model assumption, this becomes just the two additive functions here. So we have like this L of Z and some function lambda of V. And under some regularity conditions on the support of the A and V, then we can identify L. And then once we identify L, M naught, and V, then we can show that this quantity is identifiable. So that's the idea of how can we do this extrapolation. And again, just also give you more intuition why we can do this. This is actually because the help of the noise term V here. So if we go back here, even though A is not, let's say A is uniform 0, 1, but we want now to compute like the effect of Y when we observe A outside the support, right? But now because of the noise V here, you actually put like in the observed distribution, you actually see the stat value that is outside the support, because like for simplicity, you can think of V as having full support. So that also have full support. So it means that we actually see like all the range in this domain of the function L. And this is how you can do this extrapolation, even though you have like limited support for A. Yeah, that's the intuition. Okay, and now going back to our original setup where we don't actually observe that. Instead, we observe X here, which is just a linear transformation of Z. And so additionally, we need to assume that now the G naught here is injective, and we call G naught a mixing and the inverse of G naught unmixing function. And then again, the goal is to compute this conditional mean of Y given do A. And now we want to use this identifiable representation to help us achieve this task. So then first as I said, like in the first step, we want to recover Z up to an affine transformation. So now we need to define what does it mean by that. So we set an encoder, phi, f identify the unmixing function. If we can recover the latent predictor from the representation that we get by applying an affine transformation. So I think this is a standard definition of affine identifiability in the literature. And now we show that if we are given such an encoder, so if we have an encoder that f identify the unmixing function, then under assumption, this quantity of interest, so we have conditional mean of Y given do A and the conditional, also conditional interventional. So I don't know how to call this one, but basically, yeah, we condition on X and intervene on A. And these both quantities are identifiable from the observational distribution, given the knowledge of this encoder that identify the unmixing function. And once we have this encoder, then we can construct the corresponding estimator using the method of control functions as I described earlier in the case where we actually observe that. So this all good. Then the last part is to show that.
Before we go on, I just want to make sure that I'm tracking it correctly. So you first showed that like if I have if Z was transformed by some linear map, then this is identifiable. And then you say, okay, but hang on a second. If I just get an encoder that is affine identified, then in some sense that just gives me the Z that is gives me a linear map. So then the sort of same argument goes through from before.
Yes, yes, that's exactly right. Yes. And now, yeah, and I think so. And I think this is also like because we connect these identifiability requirements sort of like to the tags that we want. So this is one way to say, okay, if this is the tags we want to do this intervention extrapolation, and we also say that is this enough to just recover up to affine transformation instead of some other identifiability result that we may want. So this is also one way to think about it as well. And now the last part is to you may ask like whether we can actually obtain such an encoder in our setting or not. And we show then some sufficient conditions to allow us to also identify this unmixing function up to an affine transformation. So just to remind everyone, so this is our setting, and we're gonna make use of two main assumptions. The first is the linearity from A to Z and the exogeneity of A. And this will help us to identify the unmixing function up to an affine transformation. So by exogeneity, if we look at the residual when we regressing Z on A and compute the residual, and then look at the conditional mean of A, then this has to be 0, and this is by just exogeneity of A. And next, we're going to make use of linearity assumption. So first, let us define W phi and alpha phi as a least square solution when I regress phi of x on A. And this is just a linear least square solution. So this is somehow like a force the linearity into this. And then by linearity, then we can rewrite this equation above here by just, we can then rewrite as follows. So here, if I just plug in the true unmixing function, the inverse of G naught, then I get back, basically this is Z, I can write this as this. And then the conditional mean of Z given A, because of linearity, then I can write as just a linear function where W and alpha is definable, right? And now this motivates us to define what we call linear invariance. So we set an encoder is said to be linearly invariant if this holds. So basically, if we're regressing, linearly regress phi of x on A, and then look at the conditional mean residual and look at the conditional mean of given A, then this has to be 0. And we know that this is necessary because if we plug in the true unmixing function, then this holds by this equality here. So this is necessary. So we just need to show that this is also sufficient. So if we show this is sufficient, then we sort of done. So this is identifiable because this quantity, this constraint, we can enforce from observational distribution. And yeah, so then we have a theorem saying that if we consider an encoder that satisfies two constraints, the first one is that phi is linearly invariant, and also it has to also be bijective when I limit the domain to just image of G naught. And this is a standard condition, I think, in the literature as well. then we say that under some conditions, this equation 3 is sufficient and necessary for phi to identify the unmixing function. Yeah.
I guess if we're thinking of X as high dimensional, we wouldn't usually think of an encoder as being bijective, but somehow like whichever direction we're going in, injective or surjective, like if the, I guess, mixing function is injective or something, then
yeah, I think that's why we
yeah.
only need bijective in the image of G0.
Okay.
So like,
okay.
yeah. So because like we assume that X lives in
So
this
that's
manifold,
basically,
and then yeah.
By restricting it to that, that's the same way of saying whatever I was saying. Cool.
Yeah, exactly. And yeah, and then just to give you the full assumptions that we made here. So the first one is that the mixing function is differentiable and Lipschitz continuous. And we have that the assumption on the noise as well, that it has the characteristic function has no zeros, and that the density is analytic. And lastly, A contains non-empty open subset. So A cannot be discrete, which is a bit not very satisfying, but I think it's fine for now. And yeah, so under this assumption, we can, and yeah, we show that this the constraint that we have is sufficient and necessary for phi to identify the unmixing function. And in practice, how do we then enforce these two constraints? So the bijectivity then we can enforce by reconstruction loss in the autoencoder. So we basically use autoencoder with a regularization term that enforces the first constraint. And this, because if we go back here, this is basically moment restriction. So conditional moment restriction. So we can then make use of the maximum moment restriction by Greigamon. I think he's probably in the chat as well, in the call as well. Just want to say hi. And yeah, so we can then enforce the first one using the MMR. Then yeah, so we then do this autoencoder, regularized autoencoder. And we have some algorithm. I think I'm gonna skip this. And when we go to syntactic experiment, where we first show that we can do this recovering the latent up to an affine transformation. So here we vary the intervention, the strength of interventions, meaning here how much A affects that basically. So basically we can control the strength here. And the intuition is that the stronger the intervention, the easier for us to recover the latent up to affine transformation. And here we see our method is in blue. So we can see that once if intervention strength is strong enough, then we can recover. So the R square is close to 1. But comparing to just using, let's say, VAE or vanilla autoencoder in green and red, you can see that we cannot identify the latent up to affine transformation as expected. And lastly, we also have some synthetic experiment for the extrapolation. So here we can focus on the blue one, which is our method. And again, this is quite similar to what I in the introduction, where we just want to extrapolate beyond the training range. And here we vary the training support. And you can see that for the small training support, we can extrapolate like maybe not completely outside the support, but like within some reasonable range. And once the training support is large enough, then we can then extrapolate out in a larger range. And that's the intuition. And yeah, and that's I think all I have to say, and we'll be happy to answer any questions. And these are all the reference. Thank you.
Thank you. That was great. I have a couple of questions, but I want other people to go first.
Kick us off if you want with a very basic question. You said that A has to be just has full support, like A can't be discrete. How does that map with the intuition that you provided earlier, where like V kind of fills out the support of Z? Kind of what goes wrong with the discrete A?
Yeah, so I think it's not. Yeah, that's a good question. So I believe that this is not a necessary condition. So I believe that, I think mainly because we look at the conditional moment restriction. But okay, my intuition, but it can be completely wrong. If we look at the full independence, let's say that the residual is independent of A, I think we may be able to allow for discrete A, but we try to work out, but it got a bit messy, and then in the end we basically use the conditional moment restriction, and this you cannot work with. You cannot use this for discrete A.
I see. Is this going to be like a completeness condition kind of issue where you need to push, like we're using those conditional moments? I don't know, like in IV, you often need these complete statistics, which means you need to see a lot of variation from the instruments in order to identify things.
Yeah, something. So I think the idea is that if A discrete, then now I think this can hold for any actually phi if A discrete.
Yeah.
And because of this discreteness of A. So I think that's the main problem.
Yeah.
Okay. And yeah. But again, I think even though A is continuous, but it doesn't have full support, right? So A can be, for example, uniform 0, 1, and now we want to push outside the support. Yeah.
Cool.
This is something else on, I guess, the role of V here. So like in the identifiability case, having full support is enough. But I guess if you want to like go more into a statistical analysis of this, it would really matter how much variation you got from V, and then, something about the distance between, I guess, the distribution of Z under different values of A. Have you thought about that, or like run experiments where you vary how much, like, the variance of V or something?
Yeah, I think that's a great question. And definitely in like finite sample regime, then we somehow want the variance of V to be large enough. And so we did some experiment to vary it, and we see that the effect that if V has too small variance, then we cannot really extrapolate much from the training range, which is sort of expected, I think.
Yeah. So experimentally, it matches the intuition.
We didn't really like in terms of the theory, we didn't really investigate that much in direction. But I think that's a really valid point.
Interesting future work, probably. Yeah, and almost like I guess they're all related. I mean, like, I'm also thinking of like if you could get partial identifiability results, if like V wasn't full support, but has variation along like some, maybe subspace where there's only one direction where there's no variation, then like maybe depending on M0 or something, then you could still extrapolate for like some values
In
of
that
A, but
direction.
not others. Yeah, you can extrapolate in some directions.
Yeah. I think that's just. So let me think. Yeah, I think that's probably, you're probably right. So let's say doesn't have full support, but let's say it has full support in just one direction.
Mhm.
And I think we can work it out to show that then we can then extrapolate A in that direction. But the question is, can we identify that direction or not? Probably we can, yes. Yeah, if we
Because at some point you're
recover.
recovering the distribution of V's, so
Yeah, but like in the end, we don't actually recover the distribution of V, but it's more like a affine transformation of it because of this affine infallibility. So that's why I'm a bit unsure which do we. But I think that's also a very good point. That,
Any other questions? Oh, Kirk.
Hi. Yeah, I'm just curious because so for extrapolation, would it help if instead of requiring identifiability, you instead require partial identifiability? Would that somehow weaken the assumption that you would need to make, for example? And I think that would also be a reasonable requirement to ask because maybe it would be too much to ask for exact identifiabilities outside of the support. Right.
Yes, and what do you mean exactly by, like, what type of partial identifiability that you
for example, you can
refer
say
to?
you just want to identify maybe the bound of this conditional accurate treatment effect, right? Yeah.
I see. Yes. I think definitely that's a very good point. Honestly, I don't think I have like strong intuition on how, but yeah, I think like in practice that would be actually very nice to just, because like in practice we wouldn't hope that we can extrapolate like completely beyond, but more like giving a bar would actually be sufficient, I guess. And yeah, I think that would be a very nice extension. And in terms of how that would, so we definitely can weaken some assumptions and like, but now I cannot think exactly what would be but yeah, so probably need to think a bit more, but that's a very good point. Yes.